Good morning from Pakistan. It's 8 in the morning here, so wherever you are, welcome everyone. Um, and as you can tell, or you've been told, it's a system operator's perspective today. So I was the system operator. I was head of the system operator for the last 2 years. Just finished that stint at the end of January. So I was unfortunately at the helm during two blackouts, one partial blackout, which is in October 2022, which was half the country, and the other one was a complete system-wide blackout, which Simon referred to, which was in January of 23. So climate and disaster. So just to set the stage, what do we talk about when it comes to resilience and security? Um, these two words are interchangeable, but most of the time we talk about resilience and security to mean the ability for the system to absorb a high impact, typically low frequency, but becoming frequencies is increasing. But this kind of high impact event, to ride through that event and then to recover without any real significant loss. So that's sort of what we mean by resilience in this sort of new age. This chart I put up is a little old, but it does show an interesting trend. It's from Munich Re, which is one of the largest reinsurers in the world, and it shows that these sort of catastrophic events are. I mean, we all know they're increasing. This is just showing that it is increasing quite rapidly now. And this chart is only till 2015. I'm sure if you take the last 8 years, it probably grows exponentially. What does that mean for us in the power system? Well, in Pakistan, we've seen that our infrastructure, especially our transmission and distribution infrastructure, which is not capable of withstanding such high intensity gale force winds, does crumble. So, for example, some of our designs, are there for about can sustain 160 kilometers per hour winds, but we see storms that are even more intense. And you have just some images, for example, of towers that just completely buckled and brought to their knees literally. So it's for us. We have about 9,000 kilometers of 500 kV lines and about 13,000 kilometers of 220 kV lines. That's just our extra high voltage network. So it's not possible to retrofit or fortify 20,000 kilometers of transmission lines. Certainly not overnight, and certainly not if you don't have the resources to be able to do that. So this is obviously something that is really, really important when you're designing infrastructure. The image on the top right is actually on a mountaintop. So again, if you have this kind of infrastructure on mountains or in no-go areas or hard to reach areas, it becomes extremely difficult to repair. So this kind of transmission tower, it can take 2 weeks to repair. Just getting the equipment there, getting it up there, and doing the work and getting it started again. It's just a nightmare for a transmission company, and obviously consumers don't understand the some of these sort of finer details. So then the question is, well, if we're faced with resiliency problems, if faced with climate risk, well, how secure is the system? So the first step is to obviously understand the risks and to then model the risk in a way that makes sense to you. So severity modeling it's sometimes called severity modeling, and it's basically an assessment of cascading risks and, let's say, events that you would not consider to be likely. So if you take a typical normal distribution, a bell curve, as I've shown in this example, the red one is what you typically have, and then this is what you typically use in risk modeling, because the law of large numbers suggests that as you have more and more events, they will form a sort of bell shape. But with a normal distribution, if one standard deviation is supposed to have 68% of the outcomes, two standard deviations is like 95, 98% of the outcomes. But what we see is that when you have these climate events, or these types of events, which are, let's say, extreme weather events, the likelihood of having 2 or 3 or 4, even more transmission lines disrupted, or outages that traverse a very significant part of the network would fall in what you may call like 5 sigma or 6 sigma events. Like this should not happen for once in a 10,000 years, but of course they happen very, very often. So the way we model and the way we sort of allocate resources, or the way we dispatch, keeping in mind these risks, has to change. So, for example, in this graph, you see that you can reduce your violation probability by taking certain preventive steps and arriving at a tail. In this case, you see the part that's the part of the distribution that's on the right of the black line. You can minimize that to the point where you are sufficiently happy, or maybe happy is not the right word, but you can say, okay, this is the kind of precaution that I can take without blowing up the cost of security. Because remember, when you move this line go from the red distribution to the green one, the red one, I'm assuming, is your economic dispatch. It's the cheapest it's the cheapest outcome, whether it's centrally scheduled or self-scheduled. When you deviate from that optimal outcome in order to accommodate the risks, you are increasing costs. So it's always this is why I say, how secure is the system, but what is security worth? And I give you a couple of examples here from last summer, where, for example, on the 6th of June, this is a time where we were having significant hurricanes or tropical storms, I would say, more cyclones actually, or inland cyclones. So on the 6th of June, we actually had hailstorms in the middle of Sindh province, which is in the middle of our country, where we would expect to see in June 45 degrees centigrade, but we were getting hail. So if you can imagine that, this is the absurdity of climate change and what system operators are having to deal with. So we were expecting a natural, typical ramp up towards our evening peak time, getting up from 18 gigawatts to 20 gigawatts. But instead, as windstorms and came in, they wreaked havoc on the transmission and distribution network. So, of course, without the T&D networks, there is no demand. And so instead of going up to 20 gigawatts, generation fell to 15 gigawatts. Now this happened quite suddenly, within half an hour, within an hour. And we had tons of lines, transmission lines, distribution lines that were disrupted. So it's a two-pronged problem, because it's getting the network back up and running, and it's also ensuring that your dispatch is such that you can get the generators back up and running, especially baseload generators. Similarly, just 4 days later, we had the same problem again. This time we were at 21 gigawatts. We have two peaks in our system. We have an afternoon peak, and then we have an evening peak. So we were just coming down from the afternoon peak, and then within 3 hours, we had a loss. We saw generation drop by more than 40%. So from 21 gigawatt to 12 gigawatt. Again, this is almost impossible for a system operator to let's say, plan for in operational planning. Operational planning is usually up to 24 hours ahead, and you usually use the paradigm of security constrained economic dispatch, which typically takes an N-1 contingency compliance into account. So you may have 10 or 12, 15 critical branches, and you want to make sure that your dispatch can ride through disruption of any one of those critical branches without any issues. But when you have 5 or 6 or 8 or 10 branches affected, obviously, you can't plan for that. That's just not easily done. Simon mentioned the blackouts. So this is something different. I want to highlight that as you bring renewables into the system, and if we bring more, fax devices, so flexible AC transmission systems like STATCOMs and SVCs and things like this. So these are all power electronics. They operate in the millisecond time frame. Synchronous machines, so generators operate in seconds, 2 seconds, 3 seconds. These are electromechanical, whereas power electronic devices are there you could put them in the electromagnetic domain. You see here an example of what happened to us. The two lines, the orange and the blue line, are the system frequency for the north and the south zones. We have longitudinal networks reflecting our geography, where we have about 1,500 kilometers, you could say, from one end to the other end of the network. And so we have a northern and southern zone. Most of our generation, our newer, cheaper generation is in the south, but 80% of our load is in the north. So this is a real problem for us. And I should also add that all our wind power is in the south. So we've had low frequency oscillations, we've had voltage problems, we've had different stability problems in the past, but we've always had enough time to recover from them, to keep the system stabilized. The blackout in October 2022 actually happened when we lost two major transmission lines carrying nuclear power. So we lost about 22.2 gigawatts of generation. We were still, and we weren't able to fully recover from that. We had a partial blackout, but we didn't have a complete blackout. And that was after losing two physical, transmission lines. This blackout was unique and extremely worrisome because it actually happened after we lifted wind power curtailment. And you see here the black line. So we lifted curtailment at 7:30 in the morning, and we noticed an oscillation at around 7:33. This is a low frequency oscillation that is typically around between 0.2 and 2 hertz. It just superimposes on the main 50 hertz frequency. But as this oscillation increases, you start seeing it in the main 50 hertz frequency. So that's what you see here as the two lines start deviating from each other. And then at 7:33 we noticed this, and by 7:34, 13 seconds, 7 minutes, 7 a.m., 34 minutes, 13 seconds, the system had split, and we had two islands. And then you can see after that within seconds it was all over. And this is extremely worrisome for a system operator because there's literally no coming back. There's no way to recover from something like this that happens so fast and so suddenly. So I'm just going to illustrate exactly what happened now very briefly. So here you see the network. As I said, it's a longitudinal network. We do have, as I mentioned, that system. I didn't mention, but as you can see on the headline, that says system behavior has altered quite dramatically after commissioning the HVDC link. This is power electronics. So here you see on the left the HVDC link going from the south, bus 95 to bus 34. This is about 900 kilometers. And on the right, you see the AC network also carrying power. So we had about 15 gigawatts at that time. We had approximately 2.4 gigawatts on the DC line and about 1.7 gigawatts on the AC system. All of this power going north. As I mentioned, at 7:30, we lifted curtailment. Now, the first thing was that when we lifted curtailment, we were expecting 300 megawatts of wind power. But instead, we got 600 megawatts of wind power. Now, anyone who has dealt with renewables knows that this can happen. Your best estimates, your best guesstimates cannot, save you from instantaneous gusts in wind. If the wind farms are usually between 16 and 17, these are type 3 turbines, 16 and 17 meters per second, they're pretty close to full power. So if you're at, say, 10 or 12 meters per second wind, and there's a gust which takes it up to 14, you can easily have this situation. So we were expecting 300, we got 600. When we got 600, we here I've highlighted the bus number 18 green, where the wind power was connected. And the other thing I want to show over here is that there are some dotted lines. So between 80 to 70, this is a dotted line. This is a transmission line that was faulted. So this was out of commission. And from bus 75 to bus 78, you can also see there's another transmission line. This is a 335 kilometer transmission line. This was removed for voltage control. This is another issue with the weak transmission networks, very long transmission networks, is that it's very hard to maintain voltage if you don't have generators in the middle. So from bus 95, you see these two lines in red, 70 to 62, 60 to 60. This is almost a 600 kilometer corridor. Okay, and this is essentially, we would typically have 3 parallel lines, but because of the faulted line, we only had 2. Similarly, from bus 60, when you go onwards, you see there are 2 paths. There's the yellow path or the orange path, and then there's the pink path. Again, because of the 6353 line removed for voltage control and the 7558 line removed for voltage control, where there would be 4 lines, there were 3. And this, and so 2 takeaways here is that our transmission network was much weaker than normal because of lack of transmission lines. And secondly, from bus 95 up to bus 50 or bus 42, this is almost a 1,200 kilometer distance. Now, when you're sending power over such a long distance, think of it as a very long roof without beams in the middle, without pillars in the middle. Now, we used to have pillars in the middle. There were generators at bus 53, bus 54, bus 60, bus 63. There were generators there. These were thermal generators. But with with renewables coming in and with cheaper generation coming in, these are no longer viable. This is where the affordability and the economic dispatch sort of runs into problems. So we had this 1,200 kilometer corridor, super long, extremely long roof without any pillars in the middle. It was operating at capacity, let's say 2.4 gigawatts or around 4 gigawatts total. And then we got 600 megawatts of wind. So this created low frequency oscillations, as I showed you previously, on the AC network, which then led to voltage stability as power is flowing over this very, very narrow corridor, extremely large amounts of power. It pushes the voltage down. In fact, the oscillation, along with, what is the oscillation? Very briefly, it's just the generators in the south exchanging power with generators in the north. They're not all rotating exactly in synchronism, right? So one is accelerating, the other is decelerating, then the first one is decelerating, the next one is accelerating. They're doing this, the generators in the north are doing this collectively against the generators in the south. So as the power is oscillating over this corridor, the power transfer on the lines are oscillating, and therefore the voltages on the lines are oscillating. And this brings us to our HVDC line. As the HVDC line of bus 34, you see on the left, this is a receiving end of the HVDC line. So as most of you know, AC systems are managed through frequency control. Well, a HVDC line is managed through voltage control. It's specifically at the receiving end, you need a very stiff voltage. The voltage should not move, from its nominal value. In this case, 500 kV at the AC side of the DC converter. Except with the oscillating power, the voltage is moving between 550 and 450. This is obviously massive and cannot be sustained. So this leads to HVDC converter instability, which led to HVDC blocking. And then part of the power on the DC moved onto the AC corridor. So the AC corridor, which was already stressed, got this sort of, you could say, the straw that broke the camel's back as more power. This led to a network splitting event and transient instability, which means now the generators in the north were no longer coupled with the generators in the south. And so now you have this new topology of the network where you have 2 islands. The island on the left is the island in the south, and the island on the right is the island in the north. And if you recall, I showed you initially 2 frequencies. And the line that is connected, this bus 62 on the left to bus 60 on the right, this is where the split occurs. These AC transmission lines are gone, that they've been split. The system protection has removed these lines. So the only thing holding the system together is the HVDC line. This at this point entered into frequency control mode for a little while. Power went up to 3,400 megawatts. Of course, there was so much generation in the south, but eventually, with load shedding in the north and over frequency in the south, both islands could not be sustained, and we eventually had a blackout. So this is unfortunate. So what is interesting about this is that, you know, a few years ago, in fact, IEEE has updated its definition of system stability, and they added things like converter instability in there. So this is one of those case studies, maybe, I don't know, the first one, where we've actually seen 5 different types of system stability events occur back to back in the same sort of event, and it was all caused by you know, let's say operational planning, which was not ideal. So why was the operational planning not ideal? Well, it's very simple. This is where we talk about the energy trilemma. We talk about well, how can you bring reliability, affordability, and sustainability together? Everyone struggled with this. I don't think anyone has found an answer. Pakistan is a developing country. We have had a very sharp increase in tariffs, in end consumer tariffs, end consumer prices the last few years. So as I mentioned, all our cheap generation is in the south. So we took a hit on reliability in order to ensure that we provide the cheapest possible power to consumers. So we were dispatching at 4 gigawatts, and we saved consumers a heck of a lot of money that winter, until of course we were later, well, let's say, chastised for doing that. Of course, since then we've prioritized reliability, and instead of 2.4 gigawatts, now we cap the HVDC to 1.2 gigawatts. So just this winter, just before I left in January, we had to curtail generation at 5 rupees per unit in the south and run generation at 50 rupees in the north. So we had to run, so it was a 10x increase in generation costs, simply because of ensuring this particular reliability. Last slide. Again, since we talk about restoration as well, resilience must include restoration. Of course, God forbid you do end up in a blackout or a partial blackout. Another thing we learned from this is that the cranking path, or the path that you use to form islands, has to be extremely robust and adequately tested. So you know, our hydropower, if I go back here, is in the north. These buses 2025, these are in the north, and this Tarbela is a 5 gigawatt power station, hydropower station. It's our black start. Unfortunately, we tried to black start 8 different times, starting at 8 in the morning. So first black start attempt 8 a.m., second one 9 a.m., third one 10:30, 11:40, 1 p.m., 2:30 p.m., 3:30 p.m., and it was just a nightmare. Eventually, we were able to bring an island from a different hydropower plant over here, and then synchronize this massive hydro generator using the other one. Now, this has not been the case. This has always been our sort of go-to plant for black start. But starting 2013, this is a very old power station and dam, reservoir, and dam and power station. But in 2013, they started refurbishing it, and one of the things they did was they installed digital turbine governors, and slowly they sort of upgraded most of the governors, and these had not been tested. And the team actually that had the really old sort of, let's say, tried and tested, experienced crew had also recently retired in the last 1 year. This is a government-owned public sector facility, so maybe not as well, established in certain things. But this is the problem we faced, is that the crew who was there did not adequately understand the governors. They were not isochronous governors. Isochronous governors allow you to black start much easier. These were droop control based governors. So every time we tried to put load on these governors, you would see the frequency spiral out of control. So on the left, you see, for example, the third restoration attempt at 10:30. This is with 2 units. So you start the first unit, you see the red line, you start putting some load, you connect some 11 kV feeders in the distribution company close by, and you have sort of very close control of the system frequency for this particular island. And then after a while, you see the line jumps up a little bit. This is where you add a second unit. But on the right, you can see that it was never under control. The frequency was never under control. Eventually, and this happened every single time, it just they just lost control, and the system would collapse. So this is the other thing I just wanted to mention from our experience, is that whatever your cranking path is, it has to be robust in the sense that that you can't have circuit breaker getting stuck and things like this, or other issues. It really has to be robust and adequately tested. So the crew has to be has to have the appropriate training, and the equipment has to be appropriately tested so that your restoration can be very fast. So with that, Simon, I'm going to end my presentation. So thank you very much, and look forward to some questions later.